at all times. This is what's happening at the molecular level in your digestive system all the time. And it is so, so beautiful. So we know that serine 195 and histidine 57 are at the active site. So we're showing you space is the orange, and then the green is the peptide chain. So we're showing you where the serine and the 15. So this is sort of like the two phases. So the top is that slow phase, and the bottom is that second fast stage. So what we have here, this one, is our substrate. Right here, this is the substrate. Serine has an OH. It's actually CH2OH. Histidine has this ring with the nitrogen on it. And in this amino acid, we have some hydrogen bonding going on to maintain the tertiary structure. And what's going on here is the nitrogen of the histidine is hydrogen bonded to the hydrogen of the serine. When you see a serine in a amino acid sequence, think that's probably hydrogen bonding with something, an OH. And then the nitrogen is that has the electron pair that will hydrogen bond. So this dot, dot, dot is hydrogen bonding. All right, let's talk about the substrate now. What is this called? The CN bond.
Amide.
Yeah, an amide or a peptide bond. Now, R1 is going to be a hydrophobic side chain. It's going to be an amino acid with a hydrophobic side chain. So it fits into our hydrophobic pocket. So right here, this is our hydrophobic pocket. Now, those of you that have not had organic chemistry, just kind of go along for the ride. Those of you that have had organic should be able to really understand what I'm saying here. All right, so, and I think we've covered enough for everybody to understand, but it will be more apparent to those that have had organic. So what we have is that the bond between the oxygen and the hydrogen is weakened by this hydrogen bonding. So this oxygen is a nucleophile, and it is going to nucleophilically attack the carbon of the carbonyl. Remember when we were at the beginning of the semester, all this stuff that we were learning at the beginning of the semester is coming together right here. So here we have the hydrogen bonding, we have the nucleophilic attack of the oxygen on the serine to the carbon of the carbonyl. That carbon of the carbonyl is partially positive because carbons of the carbonyl, C double bond O, are partially positive. The oxygen is partially negative. Go on, what's your question? Oh, you got it? Okay. So what we have is then the nitrogen is going to take that hydrogen during this nucleophilic attack. We're going to create a covalent bond. So this bond right here is a covalent bond. Now there's hydrogen bonding between this hydrogen and both the serine oxygen and the peptide nitrogen. Look at this carbon. It's pretty angry. It's by angry I mean unstable. It's an unstable tetrahedral intermediate. Now, what we have, why is it unstable? Look at the carbon. The carbon that was the carbonyl has the alpha carbon attached to it that's in that hydrophobic pocket, has a nitrogen, an oxygen, and another negatively charged oxygen. Not happy. Okay, that's too much going on for a carbon. It's going to break down pretty easily. So what happens is we're going to break this peptide bond because that negative charge on that oxygen is going to fold in to make a double bond. So we're going to break this. Now, why does it want to make that double bond rather than have these 4 bonds? It's because when you have a double bond, that double bond resonates and is more stable. So this product here is more stable than this tetrahedral intermediate. That's why this bond will break. Remember, to break a bond needs energy. The way I look at what's happening with this enzyme is, have you guys ever tried to open a can and you just can't do it? And then you have your 13-year-old daughter try to open it after you, and she goes, and it opens. All right, well, you don't have 13-year-old daughters, but somebody like that, and that happens a lot to me. But what it's doing is it's getting that mostly opened. Okay, it's getting it almost there, so that the reaction is a lot easier for it to happen. So the 13-year-old can come by and open it no problem. Where I was the enzyme and I got it almost all open. So here, breaking this bond by having the enzyme form this tetrahedral intermediate that's very unstable makes breaking this carbon-nitrogen bond so much easier than if it were just out on its own. Okay, so it's really getting it almost there. And then because this product is more stable, it's going to happen. So what we've done is we are breaking that bond. Now this is our slow step. So and then this half of that peptide bond goes away. So let's just review. We have the substrate, our peptide, comes in. The serine acts as a nucleophile by attacking the carbon of the carbonyl. What is this histidine acting as? It's accepting a proton. What accepts a proton? Base, right? Then what's it doing over here? It's donating a proton to the other side. So it's acting as an acid. So our serine is acting as a nucleophile, and our histidine is acting as an acid base. Why is serine acting as a nucleophile? Because the oxygen is attacking the carbon of the carbonyl on our peptide bond. Do you want me to say that again? No? You guys got that? All right. Why is the histidine acting as an acid base? Because it's accepting the proton from the serine and then donating it later. So at the end of our first stage, we've chopped our substrate. We've broken that amide bond. But the other half is stuck. It's stuck in there. All right? Second stage is getting that back out, because part of running a enzyme catalyzed reaction is that you get the empty spot back again, right? You get that enzyme free to work again. So we've got to get this out. What happens? Water comes in. So in the second stage, water comes in, acts as another nucleophile. What do we have here stuck in there? What functional group is this right here that I'm circling? Ester. I heard someone whisper. Whoever did that, I'm not going to call you out, but there's a gold star for you after class. So that's an ester. Esters, I said, they are very susceptible to hydrolysis. Hydrolysis means we're going to break that ester bond with water. So this is what's happening in the second stage, hydrolysis of an ester. So in the hydrolysis of an ester, the oxygen of the water acts as a nucleophile to attack the carbon of the carbonyl. Yes?
I think your fell off or something.
When did it happen? Just now?
Yeah.
Okay. Yeah, it turned red. Thank you. I have to change battery. This would have been.
Try switching the two batteries.
Try switching it.
Battery you need?
I need double A's. They gave me. Oh, no. These will work. Maybe. It won't work. No, nothing's happening. I'll just finish up, guys. I'll have to start this again at second stage next time. But the oxygen acts as a nucleophile to attack the carbon of the carbonyl. Remember, this is the whole idea that carbonyl is partially positive, and then it then breaks this, but the oxygen of the water is an even better nucleophile because the histidine will hydrogen bond with that nitrogen, pulling it away from the oxygen. All right. So then we have another second tetrahedral intermediate, and then it's very much like this one above. The only difference is now it's with another oxygen. All right. Instead of a nitrogen there, we're going to break this covalent bond instead of this one. All right, we're going to break this one, and we're left with this that floats out. And where are we at? We're back with the same structure in the enzyme. The same structure in the enzyme. So here at the second stage, the oxygen of the water acts as a nucleophile, where the histidine is hydrogen bonding. We're covalently bound to the serine. Yes?
Is the chemotrypsin shape changing as it goes through those stages before it gets back to where it is?
It is not changing shape. It is not changing shape. I don't believe that there's a total. Chymotrypsin is, this is very important. Chymotrypsin is non-allosteric. So it doesn't change shape. Here, we switched gears from talking about the non-allosteric and allosteric, and that's a really good and a very important point. Chymotrypsin is non-allosteric. It's a single amino acid residue. It was our example of non-allosteric, where HECase was our example of allosteric. And so here we're just using the chymotrypsin as an example of what do amino acids do in an active site. What can they do? This is just an example of looking deep inside the active site. How do amino acids work there? This one's a little bit special because it's actually forming a covalent bond. So the serine had formed a covalent bond as a result of that nucleophilic attack. The histidine, again, is acting as a base here, and then later as an acid after the formation of the second tetrahedral intermediate. This one, I feel that the second stage is probably faster than the first stage because this is even more unstable. You have 3 oxygens around here, where you only have 2 and then a nitrogen, which is slightly less electronegative. But here, I feel that this oxygen can nucleophilically attack this pretty easy, and ester to break down is pretty easy. So that's why the second stage is faster. So we're going to break this ester bond, and then here is the other half of our molecule, the other half of our substrate that is going to leave. And we are left with our enzyme that is working so well. All right, I'm going to have to repeat the second stage in the next class. And then we will end with talking about how those two were basically the two types of catalysis that we see very often: general acid base and nucleophilic substitution. I'm not going to get into the SN1 and SN2 because that's for your reading enjoyment. So, which one acted as a general acid base in our example? Histidine with that nitrogen, all right? And then, which one acted as a nucleophile? The serine. All right, we're not going to have a quiz on Monday, all right? We'll have it next Friday for both. Probably we have the test following Friday. Wow, okay.
Will the homework still be up though?
So I will put up Chapter 7 homework, but we're not going to have a quiz on Chapter 7 on Monday. We'll have it on the Friday after. But I'm not sure when the test is going to be. It's either going to be on the Monday or Friday of not next week, but the week after. 2 more weeks, we only 3 weeks before vacation, right? And this is the first year. So I had it scheduled right before vacation.
The 11th.
The 11th. So that must be the Monday, not the Friday.
No, it's on Friday the 11th.
Oh, so that's the week. So it's next Friday.
So this Friday and
Not this Friday.
Not
next Friday.
Okay. So not Friday. There's no quiz on Friday.